Okay, so in this video, I'm going to talk a little bit about simple harmonic motion and springs in particular. So we're going to start out with just an example of a typical spring kind of problem. So what we have here is a spring, a compressible spring that's attached to a box, and that box is coming in with some initial velocity. And the question is, how much will this spring compress? So like, what if this is its, if this is the starting point, if this is 0, how much distance will this guy compress before it pushes back, right? Because it's going to, for every little bit that it pushes back, it's going to, or compress, it's going to push back with that amount of force. All right. So in my mind, this is an energy conservation problem because I know I have some initial energy, and I know that what's going to happen is that this box is going to continue to move in until it slows down and comes to a stop. So my system then is my block and my spring, and those are really only the things that matter in this case, but I'm going to say that energy is conserved in that system. So I start out with some kinetic energy from the block, and I'm going to not have any potential energy from the spring because it's completely uncompressed at this point. And then it's going to go all to the kinetic energy of the block is going to go to 0 because the block's going to come to rest, and I'm going to have all potential energy stored in the spring at the end of the compression. So my kinetic energy of my block starts out with 1/2 mv squared, and my potential energy of my spring will be 1/2 k delta x squared. So I have my m, I have my v, I know my k, and the thing I'm looking for is this delta x, so let me rearrange. And first I'll notice that I can cancel out these 1/2s, like it's common with a spring problem. And so solving for delta x, then I get m over k times v squared is equal to delta x squared. All right, so now I'm just going to plug in some numbers. My mass here is 2.5 kilograms. My k value I know is 200 newtons per meter, times my velocity is 1.2 meters per second, and I'm going to remember to square that, and that's going to leave me my delta x squared. So let me plug that into my calculator. So what I get is that I get 180, oh sorry, I'm reading my numbers wrong, 0.018 meters. I was wondering, 180 meters seemed like a very big number. Let me just check my units here. So I had kilograms over, newtons can be written as kilogram meter per second squared divided by a meter, and then I'm going to multiply that by meters squared over seconds squared. So that's going to cancel my meters, that's going to cancel my kilograms. So I've got 1 over 1 second squared, so I end up second squared times meters squared over second squared. So right, I have meters squared left is equal to delta x squared, and so now I'm just going to square root that, and what I get is that the compression should be 0.13 meters when the block comes to rest. So this is when block is at rest. Okay, so this question is one that I think really helps us think through simple harmonic motion and what it means. So what I've done here is I've taken the description of the problem. So we have a mass that's hanging from a spring off the edge of a table, and below that we have some motion sensor. That's what Sonic Ranger means, a motion sensor that is hanging below the equilibrium position after the stretched. And then they start oscillating the spring. And then at some point, the Sonic Ranger starts taking data. And they tell us that graph A is the graph of the position measured by the Sonic Ranger. So one thing we notice right away is that that's starting some distance, some positive distance up. And we know that the Sonic Ranger measures this distance in the positive direction. So we know when it's going more positive, it's moving further away from the Sonic Ranger, and when it's moving closer to it, when it's decreasing its positive direction, it's moving closer to the sonic ranger. So that tells me actually that time equals 0 is not, it's still moving upwards a little bit at time equals 0, because this graph isn't quite at its maximum at time equals 0. So what they're asking me to do is think through which of these different graphs could be could be representing which different part of the motion for this oscillating mass. Okay, so I'm going to start by thinking about the velocity. So I know, like I just said, I know that the sonic ranger is going to start, or by the position, I know that it's starting, it's still moving up, and then it's cresting its maximum, and then it's starting to come back down, right? And I know that when it's moving towards its, so the force diagram for above equilibrium will be, there will be gravity pointing down always, but when it's above equilibrium, the spring will be pointing this way. So I know that when it's coming back down, the force of the spring is with it until the point where it crosses equilibrium, and so that means it should be speeding up, right, until the point where it crosses equilibrium. And equilibrium in this graph is going to be somewhere in the middle here, because we know that it's never actually going to reach the sonic ranger, so it's never going to cross a 0. Right. Okay, so the velocity graph then has to start by moving in the positive direction, but only for a minute, and then moving quickly into the negative direction and speeding up. So that's consistent right now with graph B, right? Because it's starting just barely starting in the positive direction, and then it's moving to the negative direction and it's speeding up. It's getting more negative as time goes by. So this should be graph B. Okay. So now the net force. So again, if I think about my diagram, when I'm above equilibrium, my force should be, I have the force of gravity, and my spring force should be this way always. And when I'm up below equilibrium, my force of gravity will still be down, but my spring force should be back up, right? So if originally I'm still moving up, but I'm above the equilibrium, then my spring force should be negative. And then it should stay negative until the point where I cross negative and increasing until I turn around, and then it should be negative decreasing until the point of crossing equilibrium. And when I cross equilibrium, it should switch directions to positive. So this is consistent with graph C, right? Because it starts out negative and gets bigger for just a moment, and then starts to get smaller as it moves back towards equilibrium, so it becomes less compressed, and then it gets positive as I get. So this is positive as I move past the equilibrium point and moving downwards. Oh, careful now. That was the spring. So D is asking, or C is asking me for the force exerted by the spring on the mass. How would that be different than the net force on the mass? Right, so I think I just answered spring. So this is actually C would be graph C. So let me rethink about net force. The way that that's going to be modified is that gravity is always going to point down. The point where it's going to be 0 is going to be still at the equilibrium point. It's still going to be Oh, okay, so the net force is also by graph C because gravity does oppose the force of the spring when it's when it's below the equilibrium point, but they're still going to equal each other at the point of equilibrium. And then the force of the spring is going to get bigger. So it's still going to have the same shape as the graph on graph C. All right, so D, the kinetic energy. Okay, so thinking about kinetic energy, it's going to be maximum at equilibrium, and it's going to be minimum at turnaround points. Okay, so again, I know that the spring at time equals 0 is almost to its turnaround point. So that means I'm looking for something that starts out a little bit positive, but then immediately goes to 0 as it turns around. And then it's going to get bigger and on its way to equilibrium. Except for it should never be negative because the kinetic energy will always be positive. And so, right, if none are possible, answer no. Oh, so it should be never negative, but it should also cross 0. Never negative, but it should also cross 0. So E is never negative, D is never negative, F is never negative. F never reaches 0. D does reach 0, but at the wrong place, and E does reach 0, but at the wrong place. So none should be the answer for kinetic energy. For potential energy, I get 0 at the equilibriums and max at turnarounds. So in this case, we're on our way toward a turnaround point, so it's going to be moving towards its maximum. And then it's going to take a while moving towards its maximum, but it's going to turn around and it's going to start decreasing up until the point where it hits the equilibrium until it's 0, and then it's going to increase again. So this has very much the shape of D, where it's starting to increase until the turnaround point, then it decreases down to 0 and increases again. So this one should be graph D. And the gravitational potential energy of the mass is going to change with the height. So the PE spring versus PE gravitational should be mgh. So the height's going to be getting bigger as we go up, and then it's going to be getting less, but it's never going to be negative, and it's never going to be 0. So this looks like graph F, right? Because it's going to be getting bigger as it goes up, then it's going to turn around and get less, and it's going to turn around and get bigger, and turn around and get less, etc., etc. And that should be pretty well corresponding with graph A, yes. So this way it helps you, just thinking through these different graphs should help you think about the different important points of oscillation.